Welcome to another training session of the TIA portal. In today's session, we will see how we can simulate the S7 1200 PLC using the TIA portal software and the PLC sim software. So first of all, we will open the TIA portal software. We will create a new project in it, and we can give it any name. We will give it a simulator. And next we will create the project. Now the project is created. Next we will click on the PLC programming, add new device, and we will select our S7 1200 PLC. We will select this CPU 1214. One thing I want to mention here is that please select the CPU which is having the version above 4. So this CPU has a version of 4.2. Once the PLC is added into our project, click on this project view button. Next we will expand this PLC folder. We will go to the device configuration, and here if we click on this CPU and open its properties tab and click on this Profinet interface, here you will find its Ethernet address, and by default the Ethernet address is 192.168.0.1. We can change this IP address if we want, but for today's project we will keep it as it is. And next if we click on this IO tags, here you will find the inputs and output addresses. The input addresses are starting from I0.0 and the output addresses are starting from Q0.0. Next we will go to the program blocks and we will double click on this OB1. OB1 is the organization block number 1 and it is by default added into the PLC program. Next we will drag and drop this normal open contact. We can assign this normal open contact and the input address. We will assign it I0.0. Next we will insert a coil here and we will assign it Q0.0. So this is our input and this is our output. Whenever this I0.0 input is high, it will turn on our output Q0.0. We can rename this input as push button PB, and here we can rename this output Q0.0 as output. Next thing is we want to simulate this program. So we will click on this PLC folder and click on this start simulation. It will start our PLC simulator for S7 1200 PLC. Now the PLC simulator is started, which look like this, and we will load the program into this simulator and we will start the CPU and click on the finish button. Now we will go online with our program, and now we will try to monitor this ladder. The next thing we want to do here is that we will click on this button and it will open a complete setup for this simulator. Okay, now this window is open up. We will click on this new project button and next we will create a new project in this PLC simulator. Okay, now our new project is created. We will expand this symbol tables and we will open this symbol table number 1, and if I reduce the size of these windows to see the ladder logic, next we have to add the symbols of this ladder logic into this simulator. So to do this, simply we will click on this name and we will write PB, and this simulator will automatically detect the symbols of this program. So we will click on this push button, and this PLC simulator software automatically detect this push button connection at I0.0 input. Same way we will search for this output tag, and we will click here and write output. And as you can see, both of our tags are added into our simulator. And next thing, we will reduce the size of this. And next thing I want to do here is that I want to turn on this push button I0.0. So to do this, we will click here on this button, and as you can see that this bit is now high, this input is now high, and it has turned on our output Q0.0, and our PLC simulator also shows the result. And if I turn off this input I0.0, our output Q0.0 also turns off. So this is how we can simulate the program of the S7-1200 PLC using the PLC Sim 4.0 simulator. If you want to download this simulator, the link is in the description box. You can download this software from this link. So that's all for now. If you like this video, do share, like and subscribe to my channel, and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye. Welcome to the first session of the TIA portal training. In today's session, we are going to discuss how we can create a simple project in the TIA portal. But before starting, as always, I would really like you guys to please subscribe to my channel and press the bell icon to get notification for the upcoming new tutorials regarding TIA portal training. We are covering basic, intermediate and advanced level programming in the TIA portal in these sessions. So don't forget to press the bell icon to get the notification for the upcoming video tutorials. First of all, we will open the TIA portal by double clicking on this TIA portal icon. So this new window is open up here. So first of all, we will click on the create new project, and here we can give this project any names. We can put it as first session basic, and next we will just click on the create button. So it will create a new project. Next we will add a PLC in our project. So we will click in this tab PLC programming, and here we have to create a new device. So we will click here and it will open another window. So here we have all of our controllers, CPU. So from these PLCs we can select anyone. So for today's tutorial we will open this S7-300 CPUs, and we will select 314-2DP, and here we will select this first one and click OK. So now our PLC is added into our project. Next we will click on this project view tab. So it will take us to the project view window. Here most of the work we will do, and we will expand this devices and networks. We can click on it, and here we can see our CPU is added on our project. And next thing which we want to do is here is that we will expand it here, and we will select this device configuration. We will double click on it. Our PLC is added onto our PLC rack, and we will click on it or the CPU, and we will click on these properties, and here all the properties are mentioned. We can change these as per our requirement. And if we click here in this tab IO tags, and in this window it is showing all the inputs and outputs of this CPU. This includes the analog inputs, analog outputs, digital inputs and digital outputs. Here you can see that our digital inputs are starting from I124.0, and it goes all the way up to 126.7, and the digital outputs are starting from Q124.0 all the way up to 125.7, so total of 16 digital outputs. So now we know that our digital inputs and digital outputs addresses. So next thing we want to do is to do some programming in this CPU. So to make a program, we will go to the program blocks. We will expand this folder and double click on this OB1, which is organization block 1, which is a main block. It is by default added into any CPU. We can open this one, and here you can see that already there is a network 1, and we can make a ladder logic in this network, and we can change the programming for this block from here, and it can be a ladder function block diagram and STL. So for today we will select a ladder diagram. So first of all we will insert a NO contact I124.0, which is our first digital input, and we can change the tag name as first input. And as you can see that the tag name has been changed. And next we will add a coil, output coil, and we can write its address as Q124.0, which is our first digital output, and we can rename its tag as. So we have created a simple ladder here. Whenever our first digital input is on, it should turn on the Q124.0, which is our first digital output. So whenever this input is on, it should turn on this output coil. So next thing which we want to do here is that we want to simulate our program. So to run a simulator, we have to click here. We will click here to start the simulation, and our PLC simulator is started. And first of all we will change its interface from TCP/IP to MPI. So our program will be uploaded into the simulator through the MPI bus. So we will start to search the CPU, and as you can see that it has detected our simulator. So we'll just click on this load button. It will start to compile and check for any errors in the program. If everything is okay, and now you can see that our program is ready to load. We will just click on the load button, and the program is loaded into this simulator. Now we will run this simulator, and the next thing which I want to do here is that we will go online to this simulator to check what's happening. So we'll go online by clicking on this online button, and we will monitor our ladder logic by clicking on this icon. As you can see that everything is running fine. There is no error in our CPU. Everything is green, and here we can select our output byte, which is 124, and input byte, which is also 124. So this is our first digital input, which is I124.0. Now if I turn on this one, it should energize or turn on this output, which is Q124.0 here. So we will activate our input I124.0, and as you can see that as soon as this input goes high, it has turned on our first digital output Q124.0. And here in the simulator it is also indicated that our Q124.0 bit is on. So here is the first session on the TIA portal programming. In this session we have learned how we can create a simple project in the TIA portal and how we can simulate this project using the PLC simulator. In the next session, we will see how we can use these instructions, bit logic, timers and counters, math functions. So slowly we will go through all these instructions in our upcoming sessions. So to stay connected with us, please subscribe to our channel and press the bell icon to get the notification whenever we upload the new videos regarding the TIA portal programming tutorials. So till next time, Take care and goodbye.
Today we have connected normal open green push button at the I0.0 input and normal close red push button at I0.1 input of the S7 1200 PLC. As we know that the normal open push button have a normal open contact in it. But in the PLC programming, we can use the contact of this push button as a normal open or normal close contact as many times we want. The normal open contact will remain open and normal close contact will remain closed. But when we press the green push button, the PLC input I0.0 turns on and the normal open contact closes while the normal close contact gets opened up. When we release the push button, the PLC input I0.0 turns off and the contacts in the PLC program goes back to their normal condition. Next, as we know that the normal close push button have a normal close contact in it. In PLC programming, we can use the contact of this push button as a normal open or normal close contact. As this red push button have a physical close contact in it, the PLC input I0.1 turns on. That's why the normal open contact in the PLC program remains closed and the normal close contact remains open in the normal condition. But when we press the red push button, the PLC input I0.1 turns off and the normal open contact in the PLC opens while the normal close contact closes. But when we release the push button, the PLC input I0.1 turns on again and the contacts of the I0.1 input in the PLC program goes back to the normal condition.
Welcome to the part 2 of the TIA portal training. In today's session, we are going to see how we can use normal open and normal close contacts in the ladder logic programming. But before starting, I would really request you guys to please subscribe to my channel and press the bell icon for more upcoming video tutorials. One thing I want to clear here is that any discrete device, sensor which we connect with our PLC inputs, it can be represented in the ladder diagram as normal open or normal close contact. These discrete input devices can be a emergency stop button, push buttons, limit switches or the proximity sensors, etc. If we are using this normal open contact in our program for our discrete input like a push button, so normally this contact will be open. As soon as we press our push button, this contact will get closed and it will energize any coil which is connected at the end of this rung. And if we are using this input as a normal close contact, this contact will be normally closed, and in normal condition, because this contact is closed, it will energize this coil, and as soon as we turn on our push button, this closed contact will get opened up and it will turn off our output coil. For our today's tutorial, we have connected two push buttons at the two inputs I124.0 and I124.1 inputs of the PLC, and one output LED is connected at the Q124.0 output of the PLC. So in this example, we are going to see how we can use the normal open and normal close contacts to make a simple hold on logic. So first of all, we will delete all this and we will insert a normal open contact of I124.0, which is our input push button, start push button, and we will assign this output coil as a Q124.0, which is our output 1. So next we will start the simulator and load the program into this simulator. Once the program is uploaded into the PLC simulator, we will go online with the PLC and start monitoring this simple ladder. As you can see that this is the normal open contact and it is assigned the 124.0 or start push button address, and as soon as we turn on this push button I124.0, it has energized our output Q124.0. So as soon as we turn off our start push button, this contact gets opened up and it has turned off our output Q124.0. So this is a very straightforward and simple logic. So next thing I want to do here is that I want to hold on our output Q124.0, which means that if I only press this start push button once and release this push button, the output Q124.0 should get latched on and it should remain on. So for this one, we will again go offline with the PLC and we will insert another branch here, and we will insert a NO contact and I'll connect this branch here with the main rung, and we will assign this NO contact the address of our output. And now this NO contact is a contact of this coil Q124.0. So whenever this output is energized, this NO contact will also close. So the logic here is very simple. As soon as we press our start push button, and it will energize our output Q124.0, but at the same time our normal open contact of output Q124.0 also get closed, and through this contact this output remains on even if we release the start push button I124.0. Next we will load this program into the PLC and let's see what happens. Now, as I turn on this I124.0, it has turned on our Q124.0 output coil, and its contact is also closed because we have assigned the same address to this normal open contact. And from here, this output Q124.0 is latched on. And if we release our push button I124.0, this output still remains on. And the next thing is that we cannot turn off our output Q124.0. Now to turn off our output, we have to use a NC contact here. Next, again we will go offline and insert a normal close contact here. And we can assign this as I124.1, which is our stop push button. So this push button is normally closed. Next we will load this ladder logic into the PLC again, turn off our PLC, refresh it, load the program into the PLC, run the PLC, go online with the PLC. Now you can see that as soon as I turn on again the push button I124.0, it has latched on our output Q124.0 through this normal open contact. And even if I turn off this push button, start push button I24.0, this output is still latched on. Now to turn off this one, we have to trigger this input I124.1 by pressing the start push button once. So what it will do is that it will open up this NC contact. So once this NC contact, normal close contact, is opened, it will break the logic path from here and it will turn off our output Q124.0. So let's push the stop push button once. As you can see that for a moment this stop push button gets opened up and it breaks the path, and as the logic path breaks, it has turned off our output Q124.0. So this is how we can use the normal open and normal close contacts to make logics into the PLC program. In third session, we are going to learn the rising edge and the falling edge, and together in the third session, we are going to learn how we can make a simple program to make a logic for small filling machine, box filling machine, using normal open, normal close contacts, and rising and falling edges. So that's the end of the today's session. Do share, like, and subscribe to my channel, and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye.
In the network number 1, we have connected the two inputs parallel to turn on the output Q0.0. In the network number 2, we have connected input 3 and input 4 in parallel to turn on the same output Q0.0. Now we have the same output coil Q0.0 in the network number 1 and network number 2. Let's upload the program in the PLC simulator. Let's turn on the PLC inputs I0.0 and I0.1. And the online monitoring shows that the output Q0.0 turns on, but the output of the PLC simulator Q0.0 is not turned on. This is because we have used the same output coil address in the two different networks. To avoid this programming error, we must use the output coil in the only one network. We will go offline and delete the network number 2 and insert two normal open contacts in parallel. Now, if we activate any of these inputs, Q0.0 should turn on. Let's upload the program in the PLC. Now the program is working properly and output is turning on if we turn on any of these four inputs.
In today's session, we are going to learn how we can detect the rising and falling edge of an input. First, we will drag and drop scan positive edge instruction on the ladder. This instruction has two inputs. Here we will write the bit address for which we want to detect the rising edge. In our case, we want to detect the rising edge of the I0.0 input of the PLC. The second input of the instruction, we will write the bit M0.0. Now this instruction will store the current state of the input I0.0 in the bit M0.0 and start comparing I0.0 input and bit M0.0, and whenever the input I0.0 goes high, this instruction detects a rising edge and its normal open contact closes for one PLC scan cycle. We can confirm the detection of the rising edge by holding on the output Q0.0 whenever the contact of this instruction closes. In today's session, we are going to discuss how we can detect the falling edge of an input. First of all, we will drag and drop the scan negative edge detection instruction on the ladder. This instruction has two inputs. Here we will write the bit address for which we want to detect the falling edge. In our case, we want to detect the falling edge of the I0.0 input of the PLC. The second input of the instruction, we will write the bit M0.1. This instruction will store the current state of the input I0.0 in the bit M0.1 and start comparing the input I0.0 input and bit M0.1. And whenever the input I0.0 goes low, this instruction detects a falling edge and its normal open contact closes for the one PLC scan. We can confirm the detection of the falling edge by holding on the output Q0.1 whenever the contact of this instruction closes. Welcome to the session number 3.3 of the TIA Portal training. In this session, we are going to learn how we can make a small program for the box filler machine. Before starting, I would like you guys to please subscribe to my channel and press the bell icon for more upcoming video tutorials. Today we have a box filler machine to program. This machine starts the process with the start push button I0.6 and stops with the push button I0.7. It has a conveyor to transport the box. This conveyor runs with the PLC output Q0.0. Box presence at the filling station is confirmed by the box sensor I0.0. Once the box is at the filling station, the filling valve Q0.1 opens and start filling the liquid in the box. Once the box is filled, the fill level is confirmed by the level sensor I0.1. The filling valve closes and conveyor starts again to remove the filled box and bring in the next empty box under the filling nozzle. So that's the setup for the today's tutorial. Let's go to the TIA Portal software and see that for the today's tutorial. Now let's see the program for the today's session. In the network number 1, we have a start logic. So we have a start push button I0.6. So whenever we press the start push button, it should turn on the M0.0 auto start bit. And we can turn off this M0.0 auto start bit by pressing I0.7 start push button. In the network number 2, we have a logic to start and stop the conveyor. So first of all, we will insert the auto start bit M0.0. So whenever the M0.0 start bit is on, it should turn on the conveyor Q0.0, and this conveyor should only stop when the box is present under the filling station confirmed by the box sensor I0.0. So you can see that we have used the normal close contact. So whenever the box comes under the filling station or the filling nozzle, it's sensed by the sensor I0.0, and this normal close contact will open up and it will stop our conveyor Q0.0. In the network number 3, we have a logic to open and close the fill valve. So first of all, we will insert the auto start bit M0.0, and when the box is present in front of this sensor I0.0 and on the rising edge of this sensor I0.0, it should latch on our fill valve Q0.1, and it will start pouring liquid into our box. And once the fill level is achieved, it is confirmed by this level sensor I0.1. We have used the normal close contact. So once the fill level is achieved, this normal close contact will open up and it will turn off the output Q0.1 for the fill valve, and fill valve will be closed. In the network number 4, we have the logic to start the conveyor after the box is filled. So we have an auto start bit M0.0, and once this level sensor turns on, confirms that the box is filled, it should turn on this bit M2.0 box is filled. And we have insert its normal open contact in parallel to this one, so it will latch on the bit M2.0, and we will insert this bit in parallel with this box sensor in this network number 2. So what it will do, it will start our conveyor once again to remove the filled box from the station. As you can see that this M2.0 bit is latched on. So once the box cleared the sensor I0.0, this bit will be opened up and it will unlatch this M0.2 box is filled bit. As now the box has moved away from the sensor I0.0 box sensor, this normal close contact will be again closed and it will keeps running our conveyor motor Q0.0. So this is the logic for the today's project. We will upload this project into the PLC and let's see how does it works. As soon as we press the start push button I0.6, it hold on the auto start bit M0.0 in the network 1, and this auto start bit M0.0 turns on the conveyor motor Q0.0 and box starts to move towards the filling station. As the box comes in front of the sensor I0.0 on the rising edge, it's hold on the filling valve Q0.1 in the network 3, and liquid starts filling inside the box through the nozzle. As the liquid reaches the fill level, the level sensor I0.1 turns on and normal close contact of the level sensor I0.1 unlatch the filling valve Q0.1 and stops the filling. As the level sensor I0.1 turns on, it also holds on the M0.2 bit in the network 4 to indicate the filled box. This bit M2.0 turns on the conveyor Q0.0 in the network 1 to move the box forward and exit the conveyor. The conveyor 0.0 keeps on running and brings the empty box under the filling nozzle, and the whole cycle repeats itself. That's the end of the today's video tutorial. I hope you liked today's video. Do share, like and subscribe to my channel and press the bell icon for more upcoming video tutorials. Welcome to the session number 4 of the TIA portal. In today's session, we will learn how we can make a program to open and close the shutter door using the set and reset instructions in the TIA portal. Before starting, as always, I would like you guys to please subscribe to my channel and press the bell icon for more upcoming video tutorials. Let's see the setup for the today's tutorial. First of all, we have a motor which moves in the forward direction to open the shutter door with the PLC output Q0.0. This same motor runs in the reverse direction to close the shutter door with the PLC output Q0.1. Next, we have a panel of three buttons. We have a button to open the shutter door which is connected to the PLC input I0.0. We have a red stop push button to stop the shutter movement at any place. This red stop push button is connected to the PLC input I0.1. Next, we have a button to close the shutter door. This button is connected at I0.2 input of the PLC. Next, we have installed two sensors to detect the fully open and fully closed position of the shutter door. When the shutter door reaches the down limit sensor I0.4 turns on, and when the shutter is fully open, the up limit sensor I0.3 turns on. Next, we will open the TIA Portal software and see how we can make a program for this shutter door using set and reset commands. First of all, in the network number 1, we have the logic to set on the shutter open command. So to open the shutter, we have to first insert a normal open contact of the push button I0.0, which is our open button. So whenever we press the open button, it should set on our output Q0.0. To set on our output, we will use this command set output. So we will drag and drop this command onto the ladder logic, and here we will mention Q0.0. So the logic is simple. Whenever we press the open button I0.0, it will set on our output Q0.0 and the shutter will start to open. In the network number 2, we will write the logic to reset this command. So we need to reset this output Q0.0 once the shutter is fully open. As we have discussed earlier, when the shutter is fully open, the sensor I0.3 is on. So we will insert here I0.3 sensor, which is up limit sensor, and we will reset the output Q0.0 using this sensor. So we will insert a reset command here, and we will insert Q0.0. So whenever we press this open button, which is I0.0, it will set on our open shutter command, which is Q0.0, and shutter will start to open. And once it is fully open, we can detect it by I0.3. This sensor will be turned on and this contact will be closed, and it will reset Q0.0 output, and the shutter motor will stop at the fully open position. And next thing we want to do here is that we want to stop this shutter at any position. It can be fully open, closed, or it can be a partially open. So to do this, we will insert a contact in the parallel, which is I0.1, which is our stop push button. So whenever we press the stop push button, it will also reset our output Q0.0 and shutter will be stopped there. In the network number 3, we want to make a logic to close the shutter. So first of all, we will insert a shutter close command here, which is I0.2, which is our push button. So it is a close push button. Whenever we press this close push button, we have to set on the close command. So our close command is Q0.1. Now, whenever we press this button, it will set on this close gate command Q0.1 and our shutter will start to close. We will better rename this tag as shutter. So everything will be similar. And in the network number 4, we will reset our output Q0.1. So we want to reset this output Q0.1 once the shutter is fully closed, and we can get a signal when the shutter is fully closed from the sensor I0.4. So it is also a down limit sensor. So when the shutter is fully closed, this down sensor I0.4 is on, and we can use this sensor to reset our output Q0.1. So we will mention here Q0.1. And next thing I want to do here is that I want to stop this shutter at any moment while closing as well. So we will insert a branch here. We will insert a stop push button which is I0.1, and we will link it here. As you can see that when we press the button I0.2, it should set on our Q0.1 output and the shutter should start closing. Once the shutter is fully closed, I0.4 sensor will be turned on and it will reset our output Q0.1 and it will stop the shutter motor there. And while closing, we can stop the shutter at any position by pressing stop push button. So this is the logic for the today's tutorial, and we will upload this logic into the PLC and let's see how does it works. As you can see that right now the shutter is fully closed and we want to open this shutter. So we will press the open button which is I0.0, and as you can see that now the shutter command is set on and it should stay on even if I release this push button I0.0 and the shutter will start to open. And once the shutter is fully open, this up limit sensor I0.3 will be turned on and reset our output Q0.0. And as you can see that now the output Q0.0 is turned off and the shutter motor stops at the fully open position. One thing I want to mention here is that the reset command has a priority over the set command. This means that if this reset command is on, now even if I press this open push button I0.0, it will not turn on our Q0.0 output. If you can see here on the simulator as well, even if I press the I0.0 push button, it will not turn on our output Q0.0. Now the shutter is fully open. We will now try to close this shutter. For the closing, we have the network number 3 and 4. As you can see that when I press the I0.2 push button, it has set on our output Q0.1 and the shutter starts to close slowly. And as soon as this shutter reaches the down limit sensor I0.4, it has reset our output Q0.1 and the shutter motor stops at the fully closed position. And next thing I want to test here is that let's imagine a condition that we want to stop the shutter motor at the mid position. So to do this, we will go to the network number 1 and 2, and here we will press our open push button and it will set on our output Q0.0 and the shutter has started opening. And at any position, if I press the stop push button I0.1, it has reset our output Q0.0 and the shutter motor stops at that position. So this is how we can make a logic to open and close the shutter. I hope you liked today's session. Do share, like and subscribe to my channel and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye. Welcome to another training session on TIA Portal. This is the second part of the shutter programming video tutorial series. In the previous part, we have learned how we can make a simple program to open and close the shutter door using set and reset instructions. In the second part, we will learn how we can use the timers in the TIA Portal project. Let's suppose if someone opened this shutter door and forget to close it. Now we have to write the program in such a way that if someone forgets to close the shutter door and there is no one standing in the door or inside the room, the shutter door should close automatically after 30 seconds. To measure the 30 seconds, we need to insert a timer in the ladder logic program. Let's see the setup for the today's video tutorial. It is same as the previous part 1, except we have installed a safety sensor I0.5 in the door to detect any person inside the room or in the door. Now let's see the program for the today's tutorial. The logic is same as the previous session. Now we have to insert a timer in this logic in such a way that if we don't close the door for the 30 seconds, the door should close automatically. We will go to the network number 5 and insert a normal close contact of the sensor I0.4, the down limit sensor. After that, we will insert normal close contact of the safety sensor I0.5. Next, we will insert an on delay timer. We can give it a preset value of 30 seconds. So now if the shutter is not fully closed and this normal close contact of the down limit sensor I0.4 is closed and there is nobody in front of the sensor I0.5, this will start the timer T1 and after 30 seconds the timer will turn on the bit M60.0. This bit will indicate that the 30 seconds are passed. We can insert this bit M60.0 parallel to the close button I0.2 in the network number 3. Once this bit M60.0 is on, it will set on the output Q0.1, which is close shutter command, and the shutter starts to close. In the network number 4, once the shutter is fully closed and reaches the down limit sensor I0.4, it will reset Q0.1 shutter close command. Next we will upload the project into the PLC and see how does it works. As you can see that as soon as we turn on the open push button I0.0, it will turn on the Q0.0 open shutter command and shutter starts to open. As soon as the shutter reaches the up limit sensor I0.3, it will reset the output Q0.0 and shutter motor stops at fully open position. Now if we open the network number 3 and network number 5, in the network number 5, the down limit sensor I0.4 contact is closed as the shutter is at the up limit right now. Next, there is nobody in the room or in the door, so the safety sensor contact I0.5 is also closed. This starts the T1 timer for 30 seconds, and once the timer is over, it will turn on the bit M60.0. This bit M60.0 set on the shutter close command Q0.1 in the network 3, and the shutter starts to close down. Once the shutter is fully closed, it is sensed by the down limit sensor I0.4, which turn off or reset the close shutter command in the network number 4. So this is how we can use on delay timer in the ladder logic. That's the end of the today's session. I hope you like it. Do share, like and subscribe to my channel, and don't forget to press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye. Welcome to another training session of the TIA portal. In today's session, we will learn how we can program a PLC in the ladder logic to control the pneumatic cylinder using the 5x3-way solenoid valve. We will see how we can make the logic to stop the cylinder at 3 different positions: fully retracted or home position, mid position, and fully extended or end position. Before going further in today's tutorial, if you like our videos, please make sure to press the subscribe button and press the bell icon. In this way, you will never miss our videos. Let's see the setup for the today's tutorial. We have 3 push buttons connected to the PLC inputs I0.5, I0.6 and I0.7. These push buttons will give signal to move cylinder to home, mid and end position. Next we have a 5x3-way solenoid valve to move the cylinder shaft in reverse and forward direction. This valve has 2 coils. The coil for the forward movement is connected at Q0.0 output of the PLC, and the coil for the reverse cylinder movement is connected at Q0.1 output of the PLC. Next, we have 3 reed switches connected at the cylinder body to detect the cylinder shaft position. These reed switches are connected to I0.0, I0.1 and I0.2 inputs of the PLC. Now the task is that if we press the mid position push button, the cylinder should move to the mid position. When we press the end position push button, the cylinder should extend fully up to the end position. And when we press the home push button, the cylinder should retract fully up to home position. Now let's go to the TIA Portal software and see the ladder logic. As you can see that in the network number 1, we have a logic to make request to go to the home position. In the network number 2, we have a logic to make a request to go to the mid position. In the network number 3, we have written the logic to make request for the end position. In the network number 1, when we press the home position push button I0.7 and cylinder piston is not at the home position reed switch I0.2, it will hold on the request bit home M0.0. In the network number 2, if we press the mid position push button I0.6 and the cylinder position is not at the mid position reed switch I0.1, it will hold on the request bit mid position M0.1. In the network number 3, if we press the end position button I0.5 and cylinder piston is not at the end position reed switch I0.0, it will hold on the request bit end position M0.2. In network number 4, if the request to home M0.0 bit turns on and the cylinder piston is not at the home position sensor I0.2, it will latch on the cylinder reverse command Q0.1 through its own normal open contact to turn on the reverse coil. This way the cylinder will move towards the home position reed switch. As soon as the cylinder piston reaches the home position sensor I0.2, this normal close contact will unlatch the reverse command Q0.1. Next, if the request for the mid position M0.1 bit turns on and cylinder is at end position right now, it will latch on the reverse command output Q0.1. This will bring the cylinder from the end position to the mid position sensor. When the cylinder reaches the mid position sensor I0.1, this contact opens and unlatch the Q0.1 output and cylinder stops at the mid position. In the network number 5, if the request to the end position M0.2 bit turns on and the cylinder piston is not at the end position sensor I0.0, it will latch on the cylinder forward command Q0.0 through its own normal open contact to turn on the forward coil. This way the cylinder will move towards the end position reed switch I0.0. Now as soon as the cylinder piston reaches the end position sensor I0.0, this normal close contact will unlatch the reverse command Q0.0. Next, if the request for the mid position M0.1 bit turns on and the cylinder is at home position right now, it will latch on the forward command output Q0.0. This will bring the cylinder from home position to the mid position sensor. When the cylinder reaches the mid position sensor I0.1, this contact opens and unlatch the Q0.0 output and cylinder stops at the mid position. So this is the program for the today's project. Next we will upload the ladder logic in the PLC and let's see how does it works. Right now the cylinder is at home position, so its home reed switch I0.2 is on now. As we press the mid position push button, the mid position request bit M0.1 latch on through its own normal open contact. If we come to the network number 5, here you can see that as the mid position request bit M0.1 turns on, it latch on the forward command output 0.0 and the cylinder starts to move forward towards the mid position. As soon as the cylinder reaches the mid position read switch I0.1, this contact opens and turns off the Q0.0 forward command and cylinder stops at the mid position. Next, if we press the I0.5 end position push button, it will latch on the M0.2 end position request bit. Now, if we come to the network number 5, the M0.2 latch on forward command Q0.0 and cylinder starts to move forward. As soon as the cylinder reaches the end position sensor I0.0, this normal close contact opens and unlatch the PLC output Q0.0. Next, if we want to move the cylinder back to the mid position, we have to move the cylinder shaft in the reverse direction. Now, if we press the mid position push button I0.6, it will turn on M0.1 mid position request bit. In the network number 4, the M0.1 bit turns on the Q0.1 reverse command and cylinder starts to move backward towards the mid position. As soon as the piston reaches the mid position sensor I0.1, this normal close contact turns off the output Q0.1 and cylinder stops at the mid position. Next, if we press the home push button I0.7, the bit M0.0 for the home request turns on. This bit in the network number 4 turns on the Q0.1 reverse command. As soon as the cylinder reaches the home position, the I0.2 read switch turns on and this normal close contact opens and turns off the Q0.1 reverse command and cylinder stops at the home position. So this is how we can control the cylinder with 5x3 wave solenoid valve using the PLC ladder logic. That's the end of the today's session. If you like our videos, make sure to press the subscribe button and press the bell icon to get the notification of the upcoming video tutorials. Till next time. Take care and goodbye. If we insert a normal open contact, assign it I0.0. Insert an output coil and assign it Q0.0. Now, if we turn on the PLC input I0.0, turns on the PLC output Q0.0. Let's suppose if we turn on the input I0.0, there should be a delay of 5 seconds. And after 5 seconds, the output Q0.0 should turn on. For this, we need to insert a timer in this program. We will open the instruction menu and select the on delay timer and drag it onto the ladder logic. Assign this timer any name and set the preset time as 5 seconds. Now if we turn on the PLC input I0.0, this normal open contact closes and it will start the timer. After 5 seconds are over, the timer will turn on the PLC output Q0.0. So this is how to use the timer in the TIA portal. SR latch, insert normal open contact of the start push button. Insert SR latch instruction and assign it any free bit. Next insert an output coil Q0.0. To reset the latch, we will insert the stop push button. To reset the latch, we will insert the stop push button I0.1 at the reset input of the SR latch. Now if we press the start push button, the SR latch will set on the output Q0.0. To turn off the output Q0.0, we have to press the stop push button once. It will reset the SR latch and turn off the output Q0.0. How to blink a LED using the ladder logic. In the network number 1, we have used the selector switch I0.0 to turn on the LED light Q0.0. As this LED light turns on, its normal open contact closes and starts the timer with 1 second delay. Once this timer is over, it will set on this bit M0.0. As this bit turns on, it will start the timer with 1 second delay to reset the bit M0.0. We have created the logic to turn on and turn off this bit M0.0 using these two timers. In the last, we have inserted the normal close contact of this bit M0.0 in series with the output Q0.0. As this contact opens and closes, it will turn on and off the LED with 1 second on and off delay. Let's test the logic and turn on the selector switch I0.0. As you can see that the logic is working properly and LED output is blinking with 1 second delay. Welcome to the session number 5 of the TIA portal. In today's session, we will learn how we can use the counter instructions in the TIA portal. Before starting today's session, I will request you guys to please subscribe my channel and press the bell icon for more upcoming video tutorials. For the today's session, we have a start push button I0.0 and the stop push button I0.1. When we press the start push button I0.0, it will start the conveyor Q0.0 and boxes will start to travel on this conveyor. Next, we have a proxy sensor I0 to detect the boxes. As the boxes passes in front of this sensor, PLC should count the boxes, and after 5 boxes, conveyor should stop and the counter should reset and be ready for the next cycle. Let's go to the TIA portal software and make a ladder logic for the today's problem. In the network number 1, we want to make a logic to start the motor. So we will make a simple hold on logic here. First of all, we will insert I0.0, which is our start push button. And next, we will insert a coil here and we will assign it Q0.0 PLC output, and it will turn on our motor for the conveyor. Next, if we want to hold on this one, we have to insert here a branch. We will insert a normal open contact here and we will assign it Q0.0. And we will connect this branch here. Now whenever this motor is on, this contact will be closed and this motor will be held on through its own normal open contact. To turn off this one, we will insert a normal close contact and we will assign it I0.1, which is our stop push button. In the network number 2, we want to make a counter logic to count the boxes. So first of all, we will insert here a normal open contact and we will assign it Q0.0. So whenever this motor is running, this contact will be closed. Next, we will insert here our proxy sensor, which is I0.2. And next we want to insert here a positive edge scan. So we will go to the bit logic instructions and we will insert this positive trig command. And we will assign it the bit M2.0. Next we will insert here a counter. So we will be using this count up command today and we will drag and drop this count up instruction here. And for the preset value PV, we will put here 5 as we want to count the 5 boxes. And the CV means the current value. So we will be storing the current value of this counter into the memory word 10. Now the logic here is simple. Whenever the conveyor motor is running and the box comes in front of the sensor, on every rising edge pulse, this counter will be incremented by 1. And when the counter count reaches the count 5, it will turn on a bit. We can use bit M2.1. This bit M2.1 will indicate that the number of count has reached 5. So next we will insert the normal close contact of M2.1 bit here. So when the 5 boxes have passed in front of the sensor I0.2, this bit will be opened up and it will stop the conveyor Q0.0, and we can use the same bit M2.1 to reset this counter and be ready for the next cycle. Next we will upload this program into the PLC and let's see how does it works. Next we will upload this ladder logic into the PLC and let's see how does it works. Now we will go online with the PLC and monitor our ladder logic. As soon as we press the start push button I0.0, our conveyor starts to run and box starts to move on the conveyor. And each time the box passes in front of the sensor I0.2, the counter current value is incremented by 1, and as soon as the 5 boxes passes in front of the sensor I0.2, the counter current value reaches 5 and this bit M2.1 turns on and it will reset or latch off the in-feed conveyor Q0.0 and the box stops traveling on this conveyor. And on the same time, this bit M2.1 has reset this counter current value, and this counter is now again reset to 0, and it is now again ready to count 5 boxes again. So this is how you can use the counters in the TIA portal. That's the end of the today's tutorial. Do share, like and subscribe to my channel, and don't forget to press the bell icon to get the notification for the upcoming video tutorials. Till next time, take care and goodbye. Welcome to another training session on TIA portal. In today's session, we are going to learn how we can read an analog signal from the S7-1200 PLC and how we can scale that analog signal into some usable values. As always, before starting, I would request you guys to please subscribe to my channel and press the bell icon for more upcoming video tutorials. As you can see that today we have S7-1200 PLC and we have connected analog signal generator with it, and we have connected 0 to 10 volts analog output of the signal generator to the analog input channel 0 of the S7-1200 PLC. Now let's go to the TIA portal software and see how we can make a program to read that analog signal and how we can scale the signal into some usable values. First of all, we will open the TIA portal and create a new project in it. We can give this project any name and click on the create button. Now the project is creating, and once the project is created, we will open the PLC programming tab and create a new device in it. From the drop down menus, we will open the CPU menu, and from the CPU menu, we will select the S7-1200 PLC 214-1H31 as we are using this CPU in our today's tutorial. This will add this CPU into our project. Next, we will go to the project view, and here we will open the PLC folder and open the device configuration. If we click on the CPU and open its properties, here we can see the analog input properties of this CPU. If you scroll it down, you can see the channel 0. This channel 0 input is coming into this input word 64, and this analog channel 0 is a voltage channel. This means that it can only read 0 to 10 volts, and right now the signal smoothing is selected to the 4 cycles, and we can change it to medium and strong as per our requirement. For today we will keep it only the medium with 16 cycles. This will remove some ripples and noise which is disturbing our analog signal. Next, we will go to the program blocks and open the main block OB1. Next, we will open the conversion operations. We will drag and drop the normx function. And here we will select the double integer input, and the minimum value we will insert it as 0. And in the value input, we will insert the IW64, which is our analog input channel 0. In the maximum value, we will insert 27,648. At 0 volts input, our PLC will understand it as 0. So we have entered 0 in the minimum value. And at 10 volts, our PLC will take it as 27648 value. That's why we have entered this 27648 value in our max input. Next, for the output data type, we will select the real, and in the output we will insert MD20. Now our normx function will take the analog input which is coming into the input word IW64 and normalized it from 0 to 1 and save this normalized value into the MD20 data register. Next, we will drag and drop the scalex function
input value, we will again select the real data type and we will use same MD20 data register as a value input. We can rename the MD20 data register as a normalized value so that it is more understandable. And in the minimum value, we will insert the 0.0. Right now it is giving some error. To solve this, we have to select the output data type as real as well. Next, we will insert the max as 200.0. In the out, we will insert the MD40 data register and we can rename this data register MD40 as a scaled value. The scalex function will scale the normalized value MD20 between 0.0 to 200.0 and save this scaled value into the MD40 data register. Next, we will download this project into the PLC. And once the project is downloaded, we can monitor the ladder logic. As you can see that right now the input is 0 and our normalized value is 0 and our scaled value is 0 as the input voltage is 0 volts. As you can see that now as I increase the input analog voltage, the normalized value is starting to increase and our scale function is scaling this normalized value and this scaled value is getting saved into the MD40 data register. So this is how you can use the normx and scalex functions to read and scale an analog input. In the next video tutorial, we will learn how we can generate an analog output using S7-1200 PLC and the TIA Portal software. Before leaving, I would request you guys to please subscribe to my channel and press the bell icon for more upcoming video tutorials. Welcome to another training session on the TIA Portal. In today's session, we will learn how we can generate the analog output in the S7-1200 PLC using TIA Portal software. Before starting, I will request you guys to please subscribe to my channel and press the bell icon to get the notifications for the upcoming video tutorials. First of all, we will open the device configuration menu page and open the hardware catalog. From here, we will insert an analog output onto the PLC rack. If we open the properties of this analog output card and scroll down, you can find the address of the channel 0, which is QW96. And this output channel is a channel 0 and it can generate 0 to 10 volts output. Next, we will add a new block and we will add a organization block 1, which is OB1, and we will add a block on it and we will search for the normx instruction and we will select the normx instruction and we will select the int data type for the input and the real data type for the output. Put the 0 in the minimum. In maximum, we will put the 100 and in the value we will write memory word 100, which is our input word. The memory word 100 will be used to generate the analog output. The values of the memory word 100 will be taken between 0 to 100 and normalized between 0.0 to 1.0, and the result will be saved in the out. And we will write MD40 in the out. And MD40 will be our normalized value. Next, in the network number 2, we will add the scalex instruction. We will select the real data type for the input and integer data type for the output. Next, in the minimum, we will insert 0. In the value input, we will insert the same normalized value, which is MD40. And in the max, we will insert 27648. In the output, we will enter the same output word QW96 for the analog channel 0. Now the scalex function will take the normalized value and Scale these values from 0 to 27648 and throw out the result onto the QW96 data register for the output channel 0. And our output channel 0 will generate the 0 to 10 volt corresponding to the value of the QW96 data register. Next, we will download this ladder logic into the PLC simulator. Now we can change the display format of the QW96 data register as decimal. Next, if we modify the memory word 100 and if we enter the value 10 and press OK button, you can see that we have entered the 10 in the memory word 100. The normalized value is 0.1 and it is being scaled between 0 to 27648 and the result is 2765, and this value 2765 is saved into our output data register, and the channel 0 will generate the analog output corresponding to this value in the QW96 data register. Next, again, if we modify the memory word 100 and we will modify this time to the 50 and press the OK button. As you can see that now this time the normalized value is 0.5 and the result 13824 is saved into the output QW96 data register, and the channel 0 will generate the analog output corresponding to this value in the QW96 data register. Next, if we modify the memory word 100 and this time we will enter 100, and you can see that now the normalized value is 1 and the full max value, which is 27648, is written into the QW96 data register, and this time our output analog channel will generate 10 volts. So this is how you can make a program to generate analog output using S7 1200 PLC and TIA Portal software. So that's the end of the today's session. Do share, like and subscribe to my channel and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye.
Welcome to another training session of the TIA portal. In today's session, we will try to connect an extension I/O module with the PLC over 485 communication using Modbus RTU protocol. We have an I/O module with the 2 analog inputs and 2 digital inputs and 4 digital outputs. In today's session, we will connect this I/O module with the PLC and try to read and write the IOs of this module using Modbus RTU protocol. The address of this module is 32. We set this address using these dip switches. As you can see that we have connected A and B, RX and TX terminals of the I/O module with RA and RB terminals of RS485 port of the PLC. I have installed RS485 communication card on the S7 1200 PLC. The part number is mentioned in the description. We have connected 4 to 20 mA signal generator wires at the analog input channel 1 of this module. Before starting today's video tutorial, I want to thank all of you guys to support my channel. In case if you are new to this channel, please subscribe to my channel and press the bell icon to get the notification of the new uploaded videos. We will open the TIA portal and create a new project in the TIA portal. Once the project is created, we will go to the project view. Next, we will add a new device, expand the CPU folder and select the correct part number of the PLC. Next, we have to add the RS485 communication card on the PLC. Expand the communication boards folder and select the 485 card and drag and drop it onto the PLC. Next, we will select the PLC and click on the Properties tab. Here we have to enable the system memory bits and memory clock bits. We will enable the system memory bits and we can use the memory byte 1000. Next, we will enable the clock memory bits and enter the memory byte 1001. This byte will be used for the clock bits. Next, we will open the organization block number 1. From the communication menu, go to the Modbus folder and drag and drop the COM load function onto the ladder. This function will be used to initialize the RS485 port of the PLC. Next, we want to enable this function only one time when the PLC powers on. So we will put the first scan bit at the request input of this function. Now this function will enable only in the first PLC scan cycle. Once the RS485 port is configured, this function disables. Next, we will select the port to be configured. We will write the local in the port and select the local 1241 RS485 port. Next, enter 9600 in the baud rate and 0 in the parity. Because the I/O module is also communicating at 9600 baud rate and 0 parity bit. Next, we will drag and drop the MB master function on the network number 2. We will copy the DB name of this function and paste it at the MBDB input of the COM load function. This will link both functions together. Next, we will enter the address of the I/O module in the MB address input. The address of the I/O module is 32, so we will enter 32 as the address input. We will enter 0 in the mod as we want to read the data over the Modbus. If we want to write the data over the Modbus, we will enter 1 in the mod input. Next, we have to enter the data address which we want to read. If you see the memory address table for the Modbus RTU, you can see that the data register for the analog inputs starts from 30001. So we will enter 30001 as a starting address in the data address input. As this I/O module have only 2 analog inputs, so we want to read only the 2 registers. So we will enter the 2 in the data length input. Next, this function need a data block to save the read data for the analog channels. So we will create a data block. Next, we will open the properties of this data block, and from the attributes menu, we will disable the optimize block access option. Next, we will create the tags to save the data. We can give it any name as analog channel data. Data type will be array of the 2 integers. Next, we will create 2 boolean bits, done and error. We will use and discuss these bits later in this video series. Next, we will create data tag status with the data type as word. This status tag will show the hex codes for the status and the errors of the Modbus communication. Next, for the data pointer, we will select the analog channel data array. Now the Modbus master function will write the current values of the analog input channels in the data array. Next, we will drag and drop the done bit tag in the done output of the COM load function. Once the configuration of the RS485 port is done, this bit will turn on. Next, we will insert the 2 normal open contacts in the network number 2. In the first normal open contact, we will assign it this done bit. In the second normal open contact, we will insert the 1 Hz clock bit. This clock bit will turn on and off every 1 second. Now, when the RS485 port configuration is done, on the every pulse of the clock bit at the request input, MB master function will read the data address 30001 with data length of 2 and save the result in the data block DB3. Now the programming of the PLC is done. We will upload that program in the PLC and monitor the ladder logic. As you can see that the done bit of the comload function is true. This means that the 485 port is configured without any error. MB master function is also working properly and the busy bit gets turned on and off on the each clock pulse at the request input of this function. You can see that the communication between the PLC and IO module is also established. If we open the data block 3 and monitor the tags, expand the analog channel data array, you can see the data for the two analog channels. We have connected 4 to 20 milliamps signal generator at the channel 1 of the IO module. If we increase the current signal, the value of the channel 1 is also increasing. So this is how we can connect and communicate through the Modbus RTU protocol. In the next video, we will see how we can read and write the digital input and outputs using Modbus communication. That's the end of the today's tutorial. I hope you like it. Do share, like and subscribe to my channel and press the bell icon for more upcoming videos. Till next time, take care and goodbye. Welcome to the part 2 of the Modbus communication with S7-1200 PLC. In part 1, we have learned how to configure and program S7-1200 PLC to communicate with extension IO module and read analog input signals or Modbus communication protocol. In case you missed to watch the part 1 of this tutorial series, I would request you guys to please watch the part 1 and come back to the part 2. The link for the part 1 video is in the description box. In today's session, we will program S7-1200 PLC to read digital inputs and write digital outputs of the extension module using Modbus communication protocol. Before starting today's session, I would request you guys to please subscribe to my channel and press the bell icon to get the notification of the newly uploaded videos. We have connected some LEDs at the digital relay outputs of this module. We have connected two selector switches at the input of this extension IO module. We will program the S7-1200 PLC using the TIA Portal software to read the status of these selector switches and turn on or off these LED lights. First of all, we will open the same project of the part number 1 in the TIA Portal. We will copy the MB master function and paste it on the ladder. Now we have two MB master function in the program. In the first MB master function, the mod is 0 as we want to read the data registers over the Modbus. If we see the data register table for the Modbus communication, you can see that the registers of the discrete input contacts starts from 10001. So we will enter 10001 on the data register input to read the status of the switches connected at the input terminals of the IO module. Next we will leave everything as it is and there is no need to change anything else. In the second Modbus DB master we will change the mod to 1 as we want this function to write the status of the outputs of this IO module. This means that this function can now send the data over the Modbus to turn on or off the LEDs. Next we have to change the data addresses as we want to write the output registers. If we see the data register table for the Modbus communication, you can see that the registers of the discrete output coils starts from 1. So we will enter 1 in the data address. Next we have to give this function a request signal. For the read function, clock bit is sending the request signal every 1 second. We will change the clock bit 5 Hz frequency to send 5 request signals to the read function to speed up the things. We will use the done bit of the read function to send request to this write function. So we will open the data block number 3 and add a new row in it. Next we will create a new tag MB master read done bit with the boolean data type. We will go back to the OB1 and here we will drag and drop the MB master read done bit at the done output of the MB master read function. Now when this function have read the data or the Modbus, this done bit will turn on. We will copy this bit and paste it at the request input of the MB master function to start writing the data over the Modbus. Now when the clock pulse comes at the request input of the Modbus function, it will start reading the register of the digital inputs. When the reading is done, this bit will send the request to the Modbus function to write the digital output register. Next we have to assign the data tags to the data pointers of both read and write functions. We will open the data block db3 and create digital input tag with the array of 2 and the data type as boolean. Next we will create the digital output tag with the array of 2 and data type same boolean. As you can see that we have created two input data tags to show the status of the two selector switches, and two output tag will be used to turn on or off the digital outputs of the extension IO card. Next we will come back to the OB1 and select the digital input array tag in the data block 3 for the data pointer for the read function. Next we will select the digital output data array tag in the data block 3 for the pointer for the read function. Now the MB master function will read the status of the digital inputs. The switch is connected at the input of the IO module. This Modbus function will write the status of the digital outputs. The LED is connected to the relays of the IO module. By taking the data from the digital output data array tags and sending this data to the extension IO module over the Modbus communication. Next we will insert network 3 and insert normal open contact and assign it one of the digital input tags from the data block 3. Next we will insert an output coil and assign it one of the digital output tags from the data block number 3. Now we have a simple logic. When the digital input 0 turns on, by turning on the selector switch, it will turn on the digital output and the LED will turn on. Now the programming is completed. We will upload this data into the PLC and monitor the data logic. As you can see that both read and write functions are working properly. If we turn on the switch connected at the digital input 0, it will close the contact and turn on the digital output coil, and our LED will turn on. Now if we open the data block 3 and monitor the data tags, you can see that if I turn on the digital input 1, its tag turns true, and when we turn off the selector switch, its tag turns to the false. So this is how we can communicate extension IO modules or any other sensor transmitter over the Modbus communication with the S7-1200 PLC. That's the end of the today's tutorial. I hope you like it. Do share, like and subscribe to my channel and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye. Welcome to another training session of the TIA portal. In today's session, we will see how we can connect and configure the Wago field bus coupler with S7-1200 PLC or Profinet using TIA portal software. Before starting, I would request you guys to please subscribe to my channel and press the bell icon for more upcoming video tutorials. As you can see that we have connected S7-1200 PLC with the field bus coupler 750-370 with Ethernet cable. We have inserted one input card with 8 digital inputs and one digital output card with 16 outputs on the Wago field bus coupler. The diagram for the connection is like this. Next we have connected a switch and one proximity sensor at the first two input terminals of the input module and the 124-volt buzzer at the first output terminal of the output card. Next we will open the TIA portal software and create a new project in it. Once the project is created, go to the options menu and click on the manage GSD files. Here we have to install the GSD file of the Wago bus coupler. Otherwise we cannot add this module into our project. You can download the GSD files from the Wago website. We will browse the folder where we have downloaded GSD file and select the folder. Select the GSD file and click on the install button. Once the GSD file is installed, click on the add new device. Here we will add CPU S7-1200. We have to select the correct part number of the CPU and click on the OK button. Once the CPU is added, we will go to the network view, and from the other field devices, we will browse to the Vago devices and drag and drop the Vago 750-370 bus coupler. Next, we will double click on the Vago module and go to the device view page. Here we will add the input and the output cards of the Vago bus coupler. Once the I/O cards are added in the field bus coupler, go back to the network view. The Vago bus coupler is not connected to any network yet, so we will add this Vago module to the PLC Profinet network. Next, we have to set the IP address of the device. We will start with the CPU, go to its properties. In the Profinet interface menu, we can see the IP address settings. We can change if we want to change the IP address, but for the today's project, we will leave it unchanged. Next, we will go back and select the Vago field bus coupler module. Here you can see the IP address 192.168.0.1. Let's suppose if we want to change the IP address to 192.168.0.5. We can change it, but we have to assign the same IP address to the Vago bus coupler as well. As we have connected Vago field bus coupler and the S7-1200 PLC to our PC via LAN card, we can access the field bus coupler and assign it the new IP address. We can use the online access option and browse the Ethernet LAN card of the PC. Here we will select the Vago module and open the online and diagnostic. Here in the function menu, we can see the IP address of the Vago module. We can change it to 192.168.0.5 and click on the Assign IP address button. It will assign the new IP address to the Vago field bus coupler module. Next, we will open the OB1 block and make some logic in it to test the communication. Before we make any logic, we will open the device configuration to check the input and output addresses of the Vago I/O modules. If we double click on the Vago module, it will take us to the device view. Here you can see that the input word addresses for the input module is starting from the 2. Output word address for the output module is also starts from the 2. Next, we will go back to OB1 and make a simple logic to turn on the buzzer using the input and output addresses of the I/O module. Now the programming is done, we will upload the project into the PLC and monitor the ladder logic. As you can see that the communication between S7-1200 PLC and the Vago field bus coupler is established over Profinet. If we turn on the switch, its contact closes in the ladder program. As we bring something of metal near to the metal detector sensor, the buzzer turns on. So this is how we can establish a communication between PLC and Vago field bus coupler over Profinet. I hope we have learned something in this video tutorial. If you like today's session, do share, like and subscribe to my channel and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye. Welcome to another training session on the TIA portal. In today's session, we will learn how we can program a logic to control a continuous process. Before starting, I would request you guys to please subscribe to my channel and press the bell icon for more upcoming video tutorials. Firstly, we have a tank with a low-level probe I0.0 and a high-level probe I0.1. Next, we have two inlet actuator valves operated by the PLC outputs Q0.0 and Q0.1. These valves are used to fill the liquid in the tank. We will first pour 50 liters of the liquid from both valves A and B. We can measure the liters using the flow meters installed on each line. These flow meters output a pulse per liter of the liquid. On the PLC, inputs I 0.2 and I 0.3. As the flow meters confirms that 50 liters of liquid fill inside the tank from both sides, the agitator runs for 50 seconds to mix these two liquids. After 50 seconds, the agitator stops and discharge valve Q0.2 opens and start to discharge the tank. As the liquid level drops below the low level probe I 0.0, the drain valve Q0.2 closes and stop draining the tank, and the whole process will once again starts to make a new batch of these two liquids. Next, we will go to the TIA Model software and see the ladder logic for this project. In the network 1, we have a start push button I 0.4 and stop push button I 0.5 to turn on the start process bit M0.0. Next, in the network number 2, we have a logic to open the inlet valves A and B. When the start process bit M0.0 is on and the liquid inside the tank is less than the high level sensor I0.1, it will turn on both valves Q0.0 and Q0.1 to pour the liquid inside the tank. In the network number 3, we have written the logic to measure the flow of the water. As the inlet valves opens, these flow meters output pulses. We can count these pulses to measure the liquid using counters. As the 50 liters liquid flow through these flow meters, M0.2 and M0.1 turns on to confirm that a required 50 liters of liquid from both lines A and B is poured into the tank, and these two bits will turn off the inlet valves A and B. Next, in the network number 4, we have a logic to control the agitator. When both liquids A and B poured in the tank, these bits will close and starts the agitator motor Q0.3. In parallel, timer also starts with 50 seconds preset time. Once 50 seconds are over, the timer will turn on the agitation done bit M0.3, and this same bit will turn off the agitator motor Q0.3. In the network number 5, we have a logic to open the discharge valve. As the agitation bit M0.3 turns on, it will turn on the discharge valve Q0.2. As the liquid level falls below the low limit probe I0.0, this bit open and turn off the discharge valve Q0.2. In the network number 6, we have a logic to restart the process and fill the tank again. As the water level falls below the low level probe by 0.0, this contact opens, and on the negative edge, the reset flow meter bit M0.5 turns on for one PLC scan cycle. This bit will reset the current values of the both counters back to 0, and this will open both inlet valve again to start filling the tank. Now let's download the program in the PLC and monitor the ladder logic. As we press the start push button I 0.4, it will turn on the start process bit M0.0 to start the tank filling process. As you can see that both inlet valves A and B are turned on to fill 50 liters of liquid in the tank, and the tank starts to fill. As the liquid flow through the flow meters, these flow meters output pulses at I 0.2 and I 0.3 inputs. These pulses will get counted by these counters. Once the 50 liters of the liquid from both flow meters is measured by these counters, it will turn on the bits M0.1 and M0.2. And these bits have turned off the liquid A and liquid B valves output of the PLC Q0.0 and Q0.1. As the liquid from both valves is poured into the tank, it starts the agitator motor Q0.3. As the 50 seconds are over, the timer turns on the agitation done bit M0.3, and this turns on the discharge valve Q0.2, and tank is now starts to drain or discharge. As the liquid level falls less than the low level limit, it closes the discharge valve. And on the falling edge of the low level sensor I 0.0 signal, it resets both counter to 0 liters and open both inlet valves A and B to start filling again, and the whole process will repeat itself again. So that's the end of the today's tutorial. I hope you like it. Do share, like and subscribe to my channel and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye.
Welcome to another training session. In today's session, we are going to learn how we can make a program for a parking lot. On the entry gate of the car parking lot, there is a car sensor I 0.0 to detect the car. There is a barrier at the entry gate to stop the passage of cars, and this barrier is operated by the PLC output Q 0.0. When the car comes at the entry door and the sensor I 0.0 senses the car, the PLC output Q 0.0 turns on for 5 seconds and barrier will stay up for 5 seconds. Once the 5 seconds are over and car is no longer in front of the sensor I 0.0, the PLC output Q 0.0 turns off and barrier come down and block the passage again. As you can see that each parking space has a sensor and each sensor is connected at the individual PLC input. The sensor for the first parking space is connected at I0.1 input of the PLC and the sensor for the last parking space is connected at I1.2 input of the PLC. There is a display on the top of the parking lot which is showing the remaining empty parking lot spaces. Now we have to make a program in the PLC in such a way that it will track each parking lot if there is a car inside the parking space or not. And the PLC program should keep track of the empty parking space numbers, and we will show the number of the available spaces on the display. As the car leaves the parking space, the available space number should be updated immediately by the PLC program. On the exit door, we have installed a car sensor I1.3. When the car comes in front of the sensor I1.3, the PLC logic turn on the barrier Q0.1 for 5 seconds. After 5 seconds, if there is no longer car in front of the sensor I1.3, it will turn off the barrier Q0.1 and the barrier will come again at the down position and block the exit door. Now let's go to the TIA Portal software and see how we can make the ladder logic for the today's project. In the network number 1, we have a logic for the car entry. Whenever the car comes in front of the sensor I1.3, it will hold on the output Q0.0 through its own normal open contact. In parallel, it will start the 5-second timer. Once the 5 seconds are over and there is no car in front of the sensor I0.0, it will turn on the bit M1.0, indicate that the car has entered safely into the parking lot. The normal close contact of this bit M1.0 and it will turn off the barrier Q0.0. Next, we will go to the network number 3. It will keep track of the parking lot. When the car is parked inside the parking lot number 1, the sensor I0.1 turn on, and on the rising edge of the sensor, the move commands get activated. It will move a 1 in the memory word 30 to indicate that there is a car inside the parking lot number 1. Next, as the car leaves the parking lot 1 on the negative edge of the sensor I0.1, it will move 0 in the memory word 30 to indicate that there is no longer car inside the parking lot number 1. Next, when the car is parked inside the parking lot number 2, the sensor I0.2 turns on, and on the rising edge of the sensor, move command gets activated. It will move 1 in the memory word 32 to indicate that there is a car inside the parking lot number 2. Next, as the car leaves the parking lot 2 on the negative edge of the sensor I0.2, it will move 0 in the memory word 32 to indicate that there is no longer car inside the parking lot number 2. As you can see that we have written the same logic for all 10 parking spaces. If there is a car inside the parking space, the sensor on the positive edge will push 1 into the corresponding word. When the car left the parking space,
on the negative edge of the sensor, the move command will push 0 in the corresponding memory word. Next, if we come down to the network number 4, here we have used the add instruction to sum all data registered for the parking lots and save the result in the memory word 20. This will be the current car count inside the parking lot. Next, in the network number 5, we have used the subtract instruction to subtract the current car count memory word 20 from 10. As we have 10 parking spaces, the result will be the total available empty spaces. The result will be stored in the memory word 50. So this is the program for the today's project. Next we will upload the project in the PLC and monitor the ladder logic. As the car comes in front of the sensor I0.0 installed at the entry gate, the entry barrier output Q0.0 latch on. In the parallel 5-second timer also starts, and the car is no longer in front of the sensor I0.0, it will turn on the bit M1.0. The normal close contact of this bit M1.0 opens and turn off the entry barrier Q0.0 output. Next, in the network number 3, as the car is parked inside the parking lot number 1, the sensor I0.1 turns on. On the rising edge of the sensor, move command moves 1 in the memory word 30. Meanwhile, the second car is also entering the parking lot. As this car is parked in the second parking space, it turns on the sensor I0.1. On the rising edge, move command moves 1 in the memory word 32 to indicate the presence of the car in the second parking space. Meanwhile, more cars are coming inside and getting parked inside the parking spaces. If we come down to the network number 4, here you can see that the add instruction is adding all the memory words corresponding to the parking spaces and save the result correct number of parked car in the memory word 20. Right now 4 cars are parked, so the counter also shows the value of 4. As more cars are being parked inside the parking lot, the memory word 20 is also updating continuously. Now the parking lot is full, all 10 spaces are full and 0 parking spaces are available. Now as the car in the parking lot number 6 leaves the sensor I0.6 and on the falling edge, move command moves 0 in the memory word 40. If we come down in the network number 4, you can see that now memory word 40 for the parking space number 6 is 0 and the current counter is 9. As this car comes near to the sensor I0.3, I1.3 at the exit barrier output Q0.1 latch on and it starts 5-second timer. Once the timer is over and the car is no longer in front of the exit sensor I1.3, it turns on the bit M1.1 and its normal close contact opens and turn off the barrier Q0.1 and barrier come down again. As another car from the parking space number 3 left, the memory word 34 for this parking space becomes 0 and the current car counter reduces to 8. Now another car from the parking space number 8 left. The memory word 44 for this parking space becomes 0 and the current car counter reduces to 7. As you can see that now the car goes inside the parking and get parked inside the parking space number 6. The memory word 40 for this parking space updated to 1 and the current car counter increases to 8. Now another car goes inside the parking and get parked inside the parking lot number 8. The memory word 44 for the parking space number 8 updated to 1 and the current car counter increases to 9. So this is how we can make a program to keep track of the parking lot, and I hope you liked today's video. Do share, like and subscribe to my channel and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye.
Welcome to another training session of the TIA portal. In today's session, we will see how we can use functions in the TIA portal. Let's imagine we have 4 pumps. The most simple way to write a program for these pumps is by making simple hold-on logic for the individual pump. As the number of pumps increases, we have to write the same logic to start the pump motor again and again. To solve this problem, we will use functions in the TIA portal. We will make the logic to start and stop the motor in the function one time only, and we can use the same function in the program as many times we want. Before going further into this tutorial, I would request you guys to please subscribe my channel. To add new function, double click on the add new block. Click on the function and press the OK button. Next, we have to add the tags for this function. We will add start, stop and motor overload bits in the input section. In the output section, we will add a motor contactor bit to turn on the contactor. In the in-out section, we will create a motor start bit. We can read and write the in-out bits. Next, we will create a simple hold-on logic to start and stop the motor using these bits which we have just created. We will close this function and go back to the OB1, drag and drop the function number 1 on the network, and you can see that the function block is created with the inputs and outputs to start and stop the motors. We will drag and drop 4 instances of this function to control 4 motors. Next, all we need is to insert the addresses of the start, stop buttons and motor overload at the input side of this function, and output address of the motor contactor at the output of this function. We will insert the addresses for all 4 functions. Now the programming is done. We will upload this program in the PLC and monitor the ladder logic. If we press the start push button for the motor number 1, you can see that the motor number 1 turns on. You can see that the logic which we made inside the function is working properly. If we press the stop push button, the motor turns off. Same way we can turn on and off all of our 4 motors. So that's the end of today's session. I hope you liked. Do share, like and subscribe to my channel and press the bell icon for more upcoming videos. Till next time, take care and goodbye. Welcome to another training session. In today's session, we will learn how we can connect and read the analog 4 to 20 milliamp signal of this temperature transmitter. We will connect the temperature transmitter with the S7300 PLC and program this PLC with the TIA portal software. If you are interested in the PLC programming video tutorials, please check out our YouTube channel and subscribe to this channel for more upcoming video tutorials. First of all, have a look at the wiring of the temperature transmitter with the S7300 PLC. As we have a 2-wire analog transmitter, the wiring is really simple and straightforward. We have connected 24-volt power supply, temperature transmitter terminals and analog input channel 0 in series closed loop connection. Next, we will open the TIA portal software and create a new project and click on the create button. Next, we will add a new PLC device and select the correct part number of the Siemens S7300 CPU. Once the PLC is added into the project, expand the PLC folder and open the device configuration. Select the analog card of the CPU and click on the properties. Here you can see the analog IOs of this CPU. Select the channel 0 and change the analog input signal as current and set its measuring range
as 4 to 20 milliamps. Now the analog channel 0 is configured. Next we will go to the IO tags tab. Here you can see the addresses of the analog input channels. The address for the channel 0 is IW752. The analog values from the transmitter connected at the channel 0 will come in this input word 752. Next we will go to the main block OB1, and here we will open the conversion instructions and drag and drop the scale function. At in we will enter the PIW752, which is the input word for the channel 0. Next in the high limit we will enter 160.0, as the maximum range of this transmitter is 160.0. In the low limit input we will enter 0.0. In the bipolar input we can assign a memory bit M0.0. In the return value output we will enter the memory word 10 to record any errors in this scale function. In the out we will enter MD10, which is the double data register to save the scale temperature values. Now the programming is completed. We will compile and download the program into the PLC and monitor the ladder logic. As you can see that the scale function is working properly and scaling the analog 4 to 20 milliamp signal coming from the temperature transmitter between 0 to 160 degrees and showing the correct scale value at the MD40 data register. That's the end of the today's session. I hope you like it. Do share, like and subscribe to my channel and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye. Welcome to another training session. In today's session, we will learn how we can generate analog output signals with the PLC. First of all, let's see the wiring for the today's setup. We have connected wires from the 4 to 20 milliamp output channel of the PLC to the 4 to 20 analog input terminals of the SSR. Next, we have connected bulb in series with the output terminals of the SSR relay. This SSR relay can regulate the current and voltage being applied to the bulb as the input 4 to 20 milliamps signal increases or decreases. Before going further in today's tutorial, I will request you guys to please subscribe to my channel and press the bell icon for more upcoming video tutorials. We will open the same project file for the last session number 12. Here we will go to the conversion operations and drag and drop the unscale function on the network number 2. This unscale function will be used to generate the 4 to 20 milliamps analog output signal. Next we will go to the device configuration, select the CPU and open its properties. If we expand the analog IOs, here you can find the analog outputs. You can see that the channel 0 is configured as 0 to 10 volts. We can change it to 4 to 20 milliamps. Next, if we open the IO addresses, you can see that the analog output addresses starts from 752. This means that the address for the channel 0 is PQW752. Next, we will come back to the OB1 and enter MD46 at the input of the unscale function. Next 100 in the high limit and 0 in the low limit. As I want to scale and use my analog output MD46 data register values between 0 to 100%. Next we will assign the memory word 13 at the return value output to record any errors in the unscale function. In the last we will enter PQW752 at the out of the unscale function. So let's conclude whatever the real values we enter in the MD46 word between 0 to 100 will be unscaled and sent to the analog output channel word 752, and the channel 0 will generate 4 to 20 milliamp signal depending upon the value inside PQW752 output word. Now the programming is completed. We will upload the program in the PLC and monitor the ladder logic. Let's enter 50 in the MD46 word. You can see that the bulb starts to glow as the 50% voltage are applied to the bulb. Now let's enter 60 in the MD46 word. Now the bulb brightness increases. Let's enter 100 in the MD46. Now full 20 milliamps are applied to the input of the SSR relay and the bulb is fully bright. So that's how we can use the unscale function to make analog output signals. That's the end of the today's session. I hope you like it. Do share, like and subscribe to my channel and press the bell icon for more upcoming videos. Welcome to another training session on the PLC programming. In today's session, we will learn how we can use the PID continuous control function in the TIA portal. Let's see the setup for the today's tutorial. We have connected temperature transmitter with 4 to 20 milliamps output signal at the channel 0 of the S7300 PLC. And next we have a bulb which is operated by the SSR relay. This SSR relay have 4 to 20 milliamps input. This SSR is controlled by the analog output of the PLC channel 0 with 4 to 20 milliampere signal. As we have discussed analog input and analog output reading and scaling in the session number 12 and 13. In case you haven't seen these training sessions, the links are in the description box. We have placed the bulb near to the sensing end of the temperature sensor to warm up the sensor and raise the temperature. We will use the PID function to make a simple temperature controller. First of all, we will open the project file for the session number 13. As you can see that in the network number 1 we have a scale function to scale 4 to 20 milliampere signal of the temperature sensor. In the network number 2 we have an unscale function to send analog output 4 to 20 milliampere signal to the channel 0. In today's session, we will make the simple temperature controller with the PID continuous control function. We will double click on the add new block and select the cyclic block OB35 and click on the OK button. This block executes after every 100 milliseconds. Next, we will go to the PID menu, PID basic functions and select continuous control function. As you can see that this instruction has too many inputs and outputs. Don't worry, we will explain all these step by step. First of all, we will enter M0.1 bit at the manual on input. This input will enable or disable the PID manual mode. When M0.1 bit turns on, it will bypass the auto PID output and send the manual PID output signal. Next, we will assign the bit M0.2 to the P select, I select and D select inputs. This will enable all three P, I and D controllers. If we want to disable any of these controllers, we can disable that controller. But in today's tutorial, we will enable all three controllers and hence we will keep M0.2 bit turned on always. Next, we will assign MD100 double word data register at the set point input. This input will be the set point temperature. Next, we will enter MD20 double word data register at the PV in. PV means the present value of the temperature. If we go back to the OB1, you can see that the MD20 data register is the scale temperature value coming out from the scale function. Next, we will enter the MD110 double word data register at the manual input. Whatever we write in this MD110 data register will be sent as the PID output signal if we enable the manual PID mode. Next, we will enter MD120 data register at the gain input. The value of the MD120 will be the gain input for the P controller. Next, we will enter the MD130 at the TI input. The value of the MD130 will be the input value for the integral controller. Next, we will enter MD140 double word data register at the TD input. The value of the MD40 will be the input for the D controller. Next, we will enter MD40 at the LMN output of the PID function. LMN is the output signal of the continuous control function. Whatever values the PID function will write in the MD40 will be sent to the analog output channel. If we go back to the OB1, you can see that the MD40 is the analog output signal for the scale function. Now the programming is done, we will upload the code in the PLC and monitor the ladder logic. We have forced on the M0.2 bit to enable all three P, I, and D controllers. Next, we have to enter P, I, and D values. We can set these values by trial and error method. I have tested the circuit before and found some suitable values for my circuit. I will enter these values. First of all, I will enter 2.5 in the gain input, 500 millisecond in the integral input, and 10 millisecond in the D input. Next, we will enter the set point temperature. We will enter the 30 degrees set point. As you can see that the PID controller sends 100% output signal to the MD46 data register, and the bulb fully turns on and sensor starts to heat up as the temperature rises. Right now the set point temperature is 30 degrees and the current temperature is around 22.1 degrees, and the temperature is now slowly rising. As soon as the current temperature reaches the 30 degrees, the analog output of the PID function starts to decrease and try to keep the temperature around the set point 30 degrees. As you can see that now the temperature is maintained around the set point 30 degrees with 0.5 degree error. We can remove this error by fine tuning the PID parameters. That's the end of the today's tutorial. I hope you like it. Do share, like, and subscribe to my channel and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye. Welcome to another training session of the TIA portal. In today's session, we will see how we can make a simple program in the ladder logic for the car wash system. This car wash system has three stations: rinsing station, main wash station, and the air blowing station. Before discussing further, I would request you guys to please subscribe my channel and press the bell icon for more video tutorials. At the rinse station, we have a car sensor number 1, which is connected at the I0.2 input of the PLC. When the car comes in front of this sensor, the PLC will turn on the rinsing nozzles by turning on the PLC output Q0.0, and rinsing nozzles will spray the water on the car for 50 seconds. Once the rinsing is finished, the driver will move the car forward and move to the main washing station. Here, as soon as the car comes in front of the car sensor number 2, I0.3 sensor, the soap applicator Q0.1 will move one turn around the car and apply the soap on the car body. Once the soap is applied on the car, the soap applicator confirms the application by giving the signal at the PLC input I0.4. Once the soap is applied on the car body, there is a rest time for the 15 seconds. Once the 15 seconds are on, the rinsing nozzles Q0.2 opens and start washing the car to remove the soap. These rinsing nozzles will remain turned on for 30 seconds. Once the main wash cycle is over, the driver will move the car forward. As soon as the car comes in front of the sensor number 3, I0.4, the PLC will turn on the air blowers Q0.3 for 30 seconds to remove the water from the car body and dry it. After 30 seconds, the air blowers will turn off, and here the main washing cycle will be finished. Now let's see the programming for the today's car wash project. In the network number 1, we have a logic to start the cycle. So we have a start push button I 0.0. Whenever we turn on this start push button, it will turn on the cycle start bit M0.0. We have a stop push button I 0.1. When we press this stop push button, it will turn off our cycle start bit M0.0. In the network number 2, we have a logic to start the rinse cycle. When the start cycle bit is on and the car comes in front of the sensor number 1 I 0.2, it will turn on the bit M0.1, which is start cycle rinsing, and in parallel it will turn on the output Q0.0 rinsing nozzle station number 1, and this nozzle will turn on and start to rinse the car body. In the network number 3, we have a rinsing timer. When this bit M0.1 start rinsing cycle is on, it will start this timer T1, and once the 50 seconds are over, it will turn on the station number 1 rinsing completed bit, which is M0.2, and we have inserted the normal close contact of M0.2 bit here, and once the 50 seconds are over, it will turn on this bit and this contact will be opened up and it will turn off the Q0.0 output for the rinsing nozzles, and it will close the rinsing nozzles and stop throwing the water on the car body. In the network number 4, we have a soap applicator cycle. So when the station number 1 rinsing is completed, the M0.2 bit will turn on, and when this bit is on and the car comes in front of the sensor I 0.3 at the station number 2, it will turn on this bit M0.3 start soap application, and in parallel it will start the Q0.1 output of the PLC and start the soap applicator. In the network number 5, we have a soap application done signal. So when the soap applicator moves around the car one time, it will send a signal to the PLC input I 0.5 to indicate that the soap application is done. It will turn on the bit M0.4, which is soap application done bit. We will insert the normal close contact of this bit here to turn off the soap application. Next, in the network number 6, we have a rest timer for the 15 seconds. Once the soap application is done, it will turn on this T2 timer for the 15 seconds. Once the 15 seconds are over, it will turn on this bit M0.5 to start the final rinse. And in the network number 7, we have a logic for the final rinse. Once this bit M0.5 is on and the car is already at the I 0.3 sensor, it will turn on the bit M0.6, which indicates that the final rinse has been started, and in parallel it will turn on the Q0.2 bit to turn on the final rinse nozzles. In the network number 8, we have a 30-second timer for the rinse cycle. Once this bit M0.6 is on, it will start the timer for the 30 seconds. Once the 30 seconds are over, it will turn on the M0.7 bit, and we have inserted the same bit normal close contact here, and once this bit is on, it will open this contact M0.7 here, and this will turn off the final rinse nozzles Q0.2 after 30 seconds. In the network number 9, we have an air blower cycle. Once the final rinse is finished and the car comes in front of the sensor I 0.4, it will turn on this air blowing start bit, which is M1.1, and in parallel it will turn on the Q0.3 output of the PLC to turn on the air blowers. In the network number 10, we have an air blower timer, and once this bit is on, it will start this T4 timer for the 10 seconds, and it will turn on this bit air blowing done bit M1.2, and we have inserted this normal close contact here, and once this timer is over, this bit turns on and this contact will open up and it will turn off these two bits, and we have used the same bit in here as well in final rinse cycle to turn off this M0.6 bit, here as well in the soap applicator cycle to turn off this start soap application bit, and we can use the same bit here as well to turn off this cycle. We can insert the normal close contact here of the M1.2 bit, so when the final step, which is air blowing, is completed, it will turn off our start cycle bit M0.0. So this is the program logic for the today's tutorial. We will upload this logic into the PLC, and once it is downloaded into the PLC, we will monitor the ladder logic and see the whole process. As we press the start push button once, the cycle start bit turns on. As the car comes in front of the sensor I0. The rinsing nozzles output Q0.0 latched on and rinsing starts. Now as the rinsing cycle bit M0.1 turns on, it have also started the timer T1 for 50 seconds. After 50 seconds, the timer will turn on the rinsing completed bit M0.2. As the 50 seconds are over, this bit M0.2 normal close contacts open and turn off the rinsing nozzles Q0.0. In the network number 4, as the car comes in front of the car sensor I0.3, it will turn on the soap applicator Q0.1. As the soap applicator complete one turn around the car, it will send the application done signal at the PLC input I0.5. This signal turns on the bit M0.4 in the network number 5. This bit in the network number 5 starts the 15-second delay timer. After 50 seconds, the timer will turn on the bit M0.5 to start the final rinse. As the start rinse M0.5 bit turns on, it will turn on the final rinse nozzles Q0.2. As the rinsing starts, 30-second timer also starts, and once the 30 seconds are over, the timer turns on the final rinse finish bit M0.7, and the normal close contact of this bit opens and turn off the rinsing nozzles. Next, in the network number 9, as the car comes in front of the sensor I0.4, it will turn on the air blowers Q0.3 output and air blowers start to blow off any air particles on the car body. As the bit M1.1 is on now, it starts the 10-second timer. After 10 seconds, the timer turns on the bit M1.2. This bit M1.2 turns off the air blower output Q0.3 in the network number 9. Similarly, the normal close contact turn off the start cycle bit M0.0 and whole process stops. So this is how we can make a small logic for the car washer using timers and NO and C contacts. I hope you like this video. Do share, like and subscribe to my channel for more upcoming video tutorials. Till next time, take care and goodbye. Welcome to another training session. In today's session, we will learn how we can make a logic in S7-1200 PLC to calculate the RPM of the motor using an encoder. Before going further, I would like to request you guys to please subscribe my channel and press the bell icon for more upcoming video tutorials. We have connected an incremental encoder with 360 pulses per revolution to the back end of the motor shaft. The encoder shaft will rotate as the motor shaft rotates. We have connected A and B phase output wire of the encoder at I0.0 and I0.1 inputs of the PLC. If you want to see the detailed video regarding the encoder connection with the S7-1200 PLC, the video link is in the description box. Now let's go to the TIA Portal software and make a logic to calculate the RPM of the motor. We will create a new project in the TIA Portal and select the correct part number of the CPU we have. If we open the properties of the CPU and go to the high speed counters menu, here you have total 6 counters. We will enable the high speed counter number 1. Next, set the type of the counting as the frequency. Now the high speed counter will count the number of encoder pulses in 1 second. Set the operating phase as the AB counter as we have connected A and B phase wires to the PLC. The rest of the options we can keep as it is, no need to change anything else. Next, if we scroll down, we can find the IO addresses. The address of the high-speed counter number 1 is ID 1000. Next, we will go back to the main block OB1 and here we will insert the move instruction. We will move the high-speed counter value from the ID 1000 to the memory MD 1000. We can rename ID 1000 as HSC channel 1 and MD 1000 as encoder pulses in 1 second. Next, we will insert the multiplication instruction on the network number 2. We will multiply MD 1000 encoder pulses in 1 second with 60. The result will be pulses in 1 minute. We can save the result in MD10 and we can rename the tag as encoder pulses in 1 minute. Next, we will insert the division instruction. We will divide the MD10 encoder pulses in 60 seconds with 360 as we are using encoder with 360 pulses per revolution. We can save the result in MD20. The result will be the RPM. Next, we will download the program into the PLC and let's see how does it works. As you can see that as we start the motor, the logic starts to work and it is showing the RPM in the MD20 memory. So this is how we can make a logic in S7-1200 PLC to calculate the RPM of the motor using encoder. Before leaving, I would request you guys to please subscribe my channel and press the bell icon for more upcoming video tutorials. Till next time, take care and goodbye.
Welcome to another training session. In today's tutorial, we will see how we can make a program in the ladder logic to control the travel distance of the conveyor belt using the 3-phase motor with a disc brake coupled with an incremental encoder. We will be able to control and measure the distance traveled by the conveyor belt. Before going further, I will request you guys to please subscribe to my channel and press the bell icon for more upcoming video tutorials. We have a conveyor belt which is moving with a motor and a gearbox. We have coupled an incremental encoder with 360 pulses per revolution with this motor. We are using S7-1200 PLC for this project. If you want to see how we can connect an encoder with the PLC, the link is in the description box for this video tutorial. First of all, we will add a PLC in the project and open the device configuration. Now if we select the CPU and open its properties, here we will find the high-speed counters. Expand this menu and select the high-speed counter 1. Enable this counter. Type of the counting will be count. Operating phase will be AB and the counting direction will be up count. Next, in the hardware inputs, I0.0 and I0.1 inputs are already selected. We have connected the AB phase wires at the I0.0 and I0.1 PLC inputs. Next, we can read the encoder value from the input word IW1000. Let's see the programming for today's project. In the network number 1, we have a logic to read the encoder current value and convert it into the real data type. We have used the move instruction to move the current value of the encoder from ID 1000 to MD 1000 memory. Next, we have used the conversion instruction to convert the encoder value from the double integer to the real data type and save the result in the MD20 memory data register. Next, in the network number 2, we have a logic to calculate the distance traveled by the conveyor. First of all, we will calculate the distance traveled by the conveyor for one encoder pulse. The conveyor travels 15 mm for one complete turn of the encoder. As we know that we have connected the encoder with 360 pulses in one turn. So we will divide the 15 mm by 360 to calculate the distance in mm per pulse of the encoder and save the result in the MD30 memory. Next, we will multiply the current encoder value MD20 with the millimeter per pulse MD30. This will give us the total distance traveled by the conveyor MD40.
In the network number 3, we have a logic to start the motor in the forward direction. When this bit M0.3 turns on, it will turn on the PLC output Q0.0 to run the motor in the forward direction. This forward command can only be turned off if we press the stop push button M0.4 or by the bit M0.0, which indicates that the conveyor has reached the set point while running in the forward direction. In the network number 4, we have a logic to start the conveyor in the reverse direction. When this bit M0.5 turns on, it will turn on the PLC output Q0.1 to turn on the motor in the reverse direction. This reverse command can only be turned off if we press the stop push button M0.4 or by the bit M1.0, which indicates that the conveyor has reached the set point while running in the reverse direction. Now let's suppose if the conveyor is running in the forward direction, and as the conveyor motor traveled becomes greater or equal to the set point, it will turn on the M0.0 bit, and this bit will turn off the forward run command Q0.0. Now let's suppose that if the conveyor is running in the reverse direction, and as the conveyor motor traveled value becomes less or equal to the set point, it will turn on the M1.0 bit. This bit will turn off the reverse run command Q0.1. As you can see that we are reading the encoder value properly. Right now the conveyor motor is at 0.0 mm. Now let's run the conveyor motor in the forward direction. We will give it the set point of 1250 mm. Let's start the conveyor by pressing the start forward push button. The motor forward contactor turns on and the conveyor starts to move in the forward direction. As the conveyor traveled, reading reaches 1250 mm, the bit M0.0 turns on. The normal contact of this bit M0.0 opens and turn off the Q0.0 forward run command, and motor stops as 1250 mm. Now let's change the set point to 2500 mm. And again start the forward run command Q0.0 by pressing the start forward push button M0.3. As the conveyor motor traveled, reading reaches the 2500 mm, the bit M0.0 turns on, and this bit turns off the Q0.0 forward run command, and motor stops at 2500 mm. Now let's change the set point to 5000 mm, and again start the forward run command Q0.0 by pressing the start forward push button. As the conveyor traveled, reading reaches the 5000 mm, the bit M0.0 turns on, and this bit will turn off the forward run command Q0.0, and motor stops at 5000 mm. Now let's run the conveyor in the reverse direction. We will change the set point to 1250 mm and turn on the reverse run command Q0.1 by pressing the start reverse push button M0.5. And now the conveyor is running in the reverse direction. As the conveyor traveled, reading reaches 1250 mm, the bit M1.0 turns on. The normal close contact of this bit opens and turn off the Q0.1 reverse run command, and conveyor stops at 1250 mm. Now let's bring back the conveyor motor in the home position. We will change the set point to 0 mm and start again the reverse command Q0.1 by pressing the start reverse push button. As the conveyor motor traveled reading reaches 0 mm, the bit M1.0 turns on. The normal close contact of this bit opens and turns off the Q0.1 reverse run command, and motor stops at 0 mm over its home position. So this is how we can control a conveyor belt and measure the distance traveled by the conveyor belt. I hope you liked today's tutorial. Do share, like and subscribe to my channel and press the bell icon for more upcoming video tutorials. Till next time, take care.